be a small audience, but that's quite all right. Keep it cozy that way. But anyway, my name's Dr. Peter Zemek. I'm Senior Vice President, Montrose Environmental Group in the Research and Development Department, also part of the Emerging Technologies Group. So today we're going to talk about exploring the latest air technologies and methodologies to perform odor allocation using deep data analysis with an extremely sensitive proton transfer time of flight mass spectrometer, otherwise known as PTR-TOF-MS. All right, it's a very capable technology down to measure thousands of compounds down to the part per trillion levels in real time. And we'll be taking that deep data analysis and plugging it into the Sartorius Umetric software, which is a multivariate data analysis software. And we'll talk about that in a minute. All right, who is Montrose? Quickly, I'll go through this. Montrose is essentially a all-inclusive environmental engineering company. Air, water, solid waste, biogas, you name it, we're involved in it. And so this allows us to apply lots of different disciplines to solving real-world problems, of which this is one of them. All right, we have over 77 offices across the United States, the largest stack testing organization in North America. All right, enough about Montrose. All right, the city of Milpitas, California has over 1,100 individual odor complaints every year. All right, this is an awful lot of odor complaints per capita. Relatively small to mid-sized city in Northern California. And the Bay Area Air Quality Management District had hired some engineering companies to try to figure out where these odor complaints were coming from, because there are essentially 4 possible known locations of odors that surround this community. One of them being 150 million gallon per day wastewater treatment plant, which also includes biogas fermentation processes, as well as tertiary treatment. There's also a wet fermentation food processing plant, which takes all the food from the local surrounding communities and puts them into what's called a wet fermentation process, where it's essentially just piled into a vault. Right? There's 17 of these vaults, and they're very large vaults. They close the door and they allow it to ferment for a period of 17 days, right? During which time they capture the gases from the fermentation process. They capture any leachate that comes from the batches of fermenting food. And then they take that at the end of 17 days and they further compost that and sell it as a final product, as a soil bulk enhancer, as well as a fertilizer. There's also a very large municipal solid waste landfill, also located adjacent to these other 2 facilities. And lastly, this community sits at the very end of the San Fernando Protective Estuary, right, which is a very large tidal influence, approximately 3-foot tidal difference between low tide and high tide. And it is known that during low tide, the accumulation of organic material at the bottom of the estuary may be released, causing various types of odors, primarily sulfurous compounds. So the question becomes, which one of these facilities or this naturally occurring location is actually the source of these odor complaints, right? And the city's unfortunately been dealing with this issue for over 4 years now. A local engineering company came in and for the last 2 years have performed odor panels and bag collection analysis with dilution of odor in order to try to determine where the odors are actually coming from. And the results have been inconclusive at this point. So we were asked to come in with some deep data analysis and some high technology. I'll show you the results of what we found. So we were there for a period of 2 weeks. And in that period of 2 weeks, we were able to determine exactly where plumes were originating from And we were able to determine exactly what process within that facility the plumes were originating from, which makes it very easy for both the Bay Area Air Quality Management District to perform some kind of corrective measures and for the facility itself to address the odor issue itself. All right, so here, now in order for this process, this project and method to work, we need two things. We need a very capable way of measuring a large number of compounds down to extremely low levels below the human odor threshold, right, which is sometimes part per trillion measurements, as well as something that can be done in real time and actually map the area that is in fact it's collecting the samples from. The second part of the issue of the methodology requires a software multivariate analysis that allows you to look at this extremely large data set, over 1 terabyte of data, over 30,000 individual samples in real time, and allow you to perform correlation analysis between the facility fingerprint and the plume that's captured in the city itself, right? If you can do that, you can then determine what the correlations are between one facility or multiple facilities. And then you can have your answer and what the facility needs to do in order to correct the odor issue that's emanating from their facility. So the odors that we actually are in fact looking for, and the worst offenders are of course the nitrogen sulfurous compounds, the amines and the thiols, right? I'm sure everybody's heard of various amine compounds. Two of the most famous ones is cadaverine, right? That gets its name obviously from rotting corpses. And the other is putrescine, which is also a degradation product of proteins that contain nitrogen in the molecule, and as it degrades, forms more odorous compounds that are volatile. Sulfurs. Sulfurs are also a very known odorous compound. The ones that we're most interested in are the reduced sulfurs. You might know some as hydrogen sulfide, methyl mercaptan, some of the other thiols that are involved in that. And then, of course, we also have the alcohols. All right, when proteins and organic compounds degrade, the first part of the process is typically either anaerobic or aerobic degradation, and you form an oxygenated compound, which then goes to the carboxylic acid. So you add an oxygen to it, and then you add a COOH, and then that's the next step in the degradation process. Now, when this happens, you actually create some very odorous compounds, and one of the most famous ones is actually called scatol. The reason it's called scatol is because scat is waste product from mammalians or mammals as well as reptiles and other things, and of course can be quite odorous and have a unique smell. All right, so once we get all of these individual compounds that we can map in real time and their concentrations and the ratios between those specific compounds to each other, we can then determine correlations between them and sit outside each facility and fingerprint each facility at the fence line. We then take the vehicle and we take it down to the community where there are odor complaints, and we capture plumes within the city. And then we look at whether those plumes, those odorous plumes within the city, have a correlation to the fingerprint from each facility and try to assign the plume to the facility, right? So simple concept, but not so easy to do. And the way we do that is we use multivariate data analysis, and primarily a part of multivariate data analysis called principal component regression analysis. All right. I'm going to talk quickly about the proton transfer reaction time of flight mass spectrometer, PTR-TOF-MS. All right, this is a very sophisticated piece of equipment that actually takes sample air on the rate of about 50 to 70 milliliters per minute, CCM, and mixes it with a reagent gas. All right, we choose the reagent gas to mix with the sample according to what's called its proton affinity. So if the reagent gas has molecules that have proton, which is essentially a hydrogen atom. So if it has a bond to a hydrogen atom that is weaker than the target compound that we're looking for, it will actually transfer that proton, that hydrogen, to the target compound and increase its atomic mass by 1 atomic mass unit, right? Because proton equals hydrogen, hydrogen has 1 atomic mass unit, add it to the molecular weight of the target compound, you increase its mass by 1, and then you use a time-of-flight mass spectrometer, and you can tell the molecular weights of the individual species that are exiting the instrument, right? Pretty simple concept. Now, this is essentially what it looks like. It looks like a 1/3 larger size dorm room refrigerator. All right, it's completely self-sufficient. It has all of the turbomolecular pumps built into the system itself. It actually has wheels, and we can actually take this system on and off the van as we see fit. However, this one is integrated into the van for this particular project, but this doesn't mean that we don't take this off of the van. And sometimes we'll wheel it into a building and do sick building syndrome. We'll look for vapor intrusion, chlorinated compounds in basement areas. We can look at this for PFAS compounds, volatile PFAS compounds that are exiting the XAD traps. The applications for this type of technology are innumerable. All right, we've only really just scratched the surface. This odor allocation project is the first one that I know of its kind. Right? Multivariate analysis has been performed on oil spills to try to determine where those oil spills have come from. But what we've taken is we've taken that concept, we've added the PTR to it, and now we're taking that deep data set, plugging it into multivariate analysis, and then using those correlations to determine where the plumes come from. All right. So essentially, we talked very quickly about this proton transfer. So essentially, we choose a reagent gas for the target compounds we want to measure. We put it through the proton transfer machine. It goes into an ionization chamber, adds a little bit of energy, non-ionizing. And what happens is that proton jumps from the reagent gas to the target compounds of interest, and then we can measure them with the mass spectrometer. Right? Very simple, really. It can also do other things. Sometimes, and we do this for ethylene oxide analysis, which we've done quite a bit of, we will take a portion of the reagent gas, because we can turn up the energy to slightly ionizing, and we take a chunk of the reagent gas, paste it on the target compound. And we do that with ethylene oxide to distinguish between acetaldehyde and ethylene oxide because they are isomers. They have the exact same molecular weight. So you can't tell the difference in a mass spectrometer unless you can add something to that compound of the compound of interest that doesn't react with the other compound, and then you have the difference. Right? And this is exactly what we do for ethylene oxide analysis. However, for this study, we're primarily sticking to proton transfer reaction. Now, these is an example of several reagent gases that we choose to use for various types of compounds. And the green lines, or the green, red, and the different colored horizontal bars are your proton affinity levels, right? So we essentially, for target compounds that have a lower proton affinity, we have to use a more reactive gas. So we generally stick with what's called H3O, hydrogenal, and then sometimes we'll actually use more reactive compounds, the most reactive of which being the nitronium ion, right, for the reactive gas. Not really important, but I just wanted to give you a little concept of how we choose these reagent gases. Okay. We've talked about the PTR, how we get these concentrations of hundreds of different compounds. Now let's talk about how we analyze once we have that data set. So we take that data set, in this particular case, over 1 terabyte of data, and we plug it into a principal component regression analysis. And PCA is a way of taking an extremely large data set and looking for relationships within that data set that cannot typically be done by looking at the entire data set because you're looking at a forest and you just want to pull out the dogwood trees, right? It's very difficult to do without a software program that can do that and dig deep down into the data to look at correlations between ratios of different compounds and plumes that might have one or two unique species that aren't found in other plumes, right? When you're looking at over 500 different compounds, it's very hard to do that with the human eye, right? It takes hours and hours and hours and days, right? And you might even miss it. Principal component analysis regression is the way to take this huge data set, boil it down to only the correlations that actually have relationships between them. Okay? So when we're looking at different plumes, each plume is going to be unique in its own little specific way. And what we're trying to do is to find those unique features that are within a plume and then use that to figure out where that plume came from. Okay? All right, so the methodology behind this is we sit outside of each facility downwind for a period of time until we collect a fingerprint of the facility. So each facility is going to emit a whole slew of different compounds, but some of those are going to be very unique. And the ratios between compounds that might be emitted from another facility also are also going to be very unique to that facility. And this is essentially what we're doing. We're looking for unique compounds and we're looking for ratios between compounds. And we are actually looking at over 530 individual compounds, which is what we found in these plumes. So that's a tremendous amount of data. Then we actually go into the facility and we measure each process within the facility so that we can tell not only which facility it came from, but what's the correlation between the process within that facility. Is it coming from the chlorination basin? Is it coming from the anaerobic digesters? Is it coming from the fermentation vaults? Right? And then the software actually bins them into different correlation points. And then we look at that data and we can look at the correlations and it will actually point to which one of the facilities is actually causing the issue. All right, when we talk about a plume, this is essentially what a plume looks like, right? This is a concentration versus time over many different days. So if we were to sit in one area within the community and measure continuously at one data point per second, this is essentially what we saw. This is real data. You'll see every time the wind shifts and there's a plume in that particular wind parcel, you'll get a little blip. It might pick up an individual compound. That compound might be benzene, it might be xylene, it might be acetone or styrene, right? But when we capture a real plume, right, as opposed to what you might call an anecdotal plume. An anecdotal plume would be a car goes by, it doesn't burn all the fuel, so you get a little blip of BTEX coming out of it, right? That's not really a plume. It's a plume, but it's not a prolonged extended plume. When you have a prolonged extended plume, it'll look like what we see in the box over here. A prolonged group of compounds that are above ambient level geographic area concentration, right? Because every geographic area has unique ambient combination of compounds, right? Doesn't matter where you are, anywhere in the world, it's going to be unique. Right? And if that's prolonged enough and contains enough compounds, we can use it to try to determine where that plume came from if we have fingerprints to compare it to. And that's what we're doing here. And so what we did was we went to each facility and we used sample bags and then ran those through the analysis. And then we actually have a snorkel you can see here on the van. And we can either drive continuously and map an entire area, or we can sit in one location and just wait for the plume to come by us. And that's essentially most of the time what we did. We found areas that would be pertinent to the study, which would be middle schools, elementary schools, colleges, city parks, apartment complexes, places where receptors are going to be exposed, and those are where the complaints are going to come from, right? And that's what we did. We sat out there and we waited and we collect data and we collect data and we collect data. And then we run that data through the multivariate analysis. All right, so this is pretty much a city of Milpitas, and each one of these lines represents an individual location where a possible odor plume is originating from. All right, so those are odor sources, and you can see here there's some various locations throughout the city where we actually sat, some of them being at hotel parking lots, some of them being at elementary schools, and some of them at parks. All right, so once we get the fingerprint model, all right, we have to look at that, plug it into the software, and we have to look at the data, all right? And this is what we did. And so the first thing we did was look at the individual facility fingerprints and determine, one, you have to know, are these plumes unique? Because if there's nothing unique between the plumes from each facility, we can't do anything with that. So first thing we did was, let's see if the facilities are unique. And sure enough, when you plug them in and you eliminate some of the common masses that are common between facilities, like acetone happens to be very common from all those three facilities. They're all emitting acetone. Might not be a good one to look at, so we exclude that one. CO2, we exclude that. Right? NOx, not interested. Let's look at the odorous compounds and the ratios between those, and that's what we did. And so we eliminated certain masses that we know are common throughout the facilities, as well as could be coming from other manufacturing processes, because we want to keep it specific to these 4 facilities or 4 locations, right? And then we build our model. And what we do is we saw a very nice separation between the facilities. And here you can see, this is a way of what the principal component analysis actually spits out data. It spits out correlations and compares the mean of the entire data set, all of the facilities, and then looks at individual plumes and looks at the correlations between those plumes to the entire mean or the entire mass. So the bar at the bottom is the mean of all of the data, and these bars that rise above and below are the correlations for each compound within that plume, and whether it's greater than the mean or less than the mean. And the ratios of the bars also goes into the correlation. But what it told us that each one of these colored dots represents a facility, right? And each of the ones, the other ones represent individual processes within that facility. And because they fall in different quadrants of the entire universe, the mean universe, when we talk about the mean universe, you essentially can find something very unique. And so when you have good separation between those data points, that's an indication that it's unique. If all those data points lie on top of each other, then there's really nothing unique between the plumes, and it becomes very difficult to try to figure out what the difference is between those plumes. All right, so that was the first step. Everything looks good. We have a unique model. Each facility is unique. Now let's go to the community and collect data there and plug them into this model and see where the data falls. All right, and so this is really a little more granular. So each one of these represents data points within the facility. And what we do then is the ones that fall outside of the oval area, we actually exclude those, or we raise the bar so that those disappear, because we really want to focus on the real uniqueness of that plume. Remember, we're working with 530 plus individual compounds. If we throw away 100 of them, we still have plenty of data to look at. So the ones that are anecdotal, or the ones that don't seem to fit any particular model, you can eliminate those, right? And that's what we did. And that's what this represents. So I talked about the geographic area being very unique. So when you go into the community, you actually can raise the sensitivity, all right, of the analysis, because we're looking at part per trillion levels. So we want concentrations that are above odor thresholds for the human nose. And this is very interesting, but the human nose actually evolved so that it can smell compounds that will do it harm, right? Same thing with taste, right? Everyone can taste bitter. What compounds are typically bitter? The poisonous ones, right? So we learned the human body evolved not through natural selection. People that couldn't taste bitter aren't here anymore, right? So hydrogen cyanide, perfect example. There's cyanide in a food, it's going to taste bitter to you, right? So you avoid that food. So that's how you evolve. Same thing with the nose. Sulfurous compounds can be quite toxic, right? So the human nose learned when you go into a swamp, you stay away from that area because you could be overcome by the sulfurous compound. Amines, degrading proteins, right? Wanderer-gatherer wanders around and finds a dead animal, right? When did it die? Can I eat that? Well, if it smells, because of the degrading nitrogen compounds, you've learned that there's bacteria that will be harmful to you and you stay away from it. So that's how we've really evolved. So, but now we're actually have analytical equipment that can measure below the threshold of the human nose. So even though we can't smell it, it might still be there. So with this type of analytical capability, we have to actually raise the bar. And so we eliminate compounds that are at a level that really don't matter, right? So we want to look at the ones that are in the plume at the higher concentrations. And what we do is we just measure, we raise the sensitivity, and this is now 2 part per trillion as a part per billion, as opposed to, 50 parts per trillion, right? And we play with the model a little bit so that what's called the bins, all right? Now, I don't know if you can see this, and it's really small, and I apologize for that, but we try to do it so that there are going to be samples that are taken that don't fall into an individual bin, all right? So it's unassigned. And we try to raise the sensitivity so that we get the least number of unassigned samples. And again, this is more complicated than I can present in the 45 minutes here, but this actually works. You can raise the sensitivity so that you eliminate the number of unbinned samples, and you raise it so that you get more of the compounds fall into a specific bin that correlates to a particular facility, right? So if it's too low, you start to get bins into all of the facilities, but when you raise the sensitivity, you're focusing on the ones that are most associated with that elevated plume, and then they'll start to fall into bins of 1 or 2 of the facilities. And that's exactly what we did and exactly what we saw happen. And so the non-bin ones started to now fall into 1 of 2 facilities, all right? So out of the 4 locations we were looking at, we can tell right now that most of the samples from the odor plumes were associated 60% with 1 facility and 40% with another facility, right? And the other 2 facilities were not guilty, you might say, of this occurring, right? Of these plumes coming from these other 2 facilities. So 2 of the facilities had odors coming from them that were reaching the community. 2 of the other facilities did not, right? And that's what this model told us. And so when you look at this, now these are actually 4 individual plumes that were captured during the course of sampling. So we went out and we sampled hours and hours, overnight sampling continuously. And when we found a plume that was contained and elevated for a good amount of time, we took only that data set and compared it to the fingerprint analysis. And we picked 4 of them, right? Because that was the best data, most representative data. And the model told us that it was coming from 1 of those 2 facilities, but primarily mostly from 1 of the facilities. So these are the results of those 4 samples. And I don't know if you can see this, but I'll point it out. But facility B associated with those odorous plumes 90% of the time, and facility C was associated with odorous plumes 10% of the time. Right? So here, that's a pretty strong data correlation. The model is telling us that if once we build a model at the fence line of an individual of the facility, and then we go and capture plumes downwind of those facilities, we plug them into our model, a multivariate data analysis, it will sort through those plumes and tell you where they are coming from. And this particular data set tells us these 4 plumes, that one of these plumes, 90% is coming from facility B, 10% from facility C, and the 3rd plume we captured, 100% was coming from facility B and not from facility C. And the other 2 is 98% facility B, 2% facility C. And the last one was 89% and 11%, right? So this is pretty strong evidence that facility B is really causing the majority of odor events in the city of Milpitas. And this is public, so I could tell you the names of the facilities. I just choose not to because it's not for me to call out anybody. I'm just showing you the results of a very large 1 terabyte of data collected in this particular study. So the results of this study indicate that using multivariate principal component data analysis, you can build a model by sitting outside fence lines of facilities and creating fingerprints. Once you have those fingerprints, when there is an odor complaint or a non-odor complaint, you can go downwind of those facilities, you can collect that data, and you can plug it with a multivariate, with a proton transfer time of flight mass spectrometer, because you can't do this unless you have a very large data set. Right? If you're looking at 1 or 2 compounds, there's just not enough data to make a regression correlation to a facility. Here we're looking at 530 individual compounds, right? And those 530 individual compounds, the majority of those correlate to these 2 facilities. Right? Facility B being the majority of the offending odor producer. Right? So this tells us that a PTR time of flight mass spec with a principal component regression analysis, you can build a model, and then when there's an odor complaint, you can collect a Suma canister or a bag, or you can send the platform out, send the data in, analyze the data, run it through the regression correlation, and you can tell where those plumes are coming from. Right? This has never been done before. Right? A lot of this work is done using odor panels, right, with subjective subjects that are looking at dilutions. All right, they're diluting plumes to get the odor threshold, and then they're describing the plume. Is it pungent? Is it sweet? Is it skunky? Is it musty? Right? And then they're trying to correlate that subjective data to a particular facility. All right, that is going to be much more harder to defend than something that has a deep data analysis with capability of analyzing down over 530 compounds down in the part per trillion level. All right, and looking at the regression correlations. And principal component regression is used in the manufacturing sector for many, many decades, right, to determine quality control, quality assurance. And this is essentially what we're doing. We're looking at the quality control and quality assurance of a detached plume and correlating it back to a fingerprint from a facility. All right, any questions? Sure. Yeah, we actually have both. So there are a few compounds that are very unique to a particular facility, like isoprene is one of them, right? And then it's interesting because we see from the wastewater treatment plant, we see more sulfurous, oxidized sulfur compounds, right? From the wet fermentation, obviously there are more amine. From the estuary, we're seeing more reduced sulfurs. So there are classes of compounds too that are making this rather easy because right, if there aren't unique compounds, then you fall back on the ratios. The correlations might not be as strong, but it's certainly going to correlate to a particular facility or not. But one thing you have to worry about is the farther away you get away from a facility, then you run the risk, and the risk is really what compounds are either transferring, being converted to something else between the facility fence line and the community, or are they not making it, right? Sulfur's got a molecular weight of 32. It's a heavy compound, right? They tend to go down. The lighter ones tend to loft up and stay in the air longer, so they're going to get farther away. And that's the only risk that you have to worry about with this type of analysis, is whether that plume and those compounds are going to make it to the place that you're collecting the odorous plume and then trying to correlate back to the fence line. Yeah. Yeah, it's hours and hours and hours of looking at the data and making sure the K factors are correct so that the concentrations are correct. And then also isomers. You have to worry about isomers, right? Because, you know, like I said, you can't tell the difference between ethylene oxide and acetaldehyde. They're the same molecular weight. So for isomers, we would tend to throw out those compounds because it might be a different compound and we might get a different correlation. So when something that's subjective like that, since we have so many compounds to work with, we're looking at part per trillion levels here, we just eliminate them. And that was that process of throwing out certain masses that are common to all the facilities, or ones that we know will not make it there, like, you know, some of the PAHs, you know, they're not going to get very far from the facility. Yeah. The important ones we actually, we do analysis for. We actually shoot and we get a slope, which is your K factor of the calibration curve. But there's plenty of published K factors that we do use, and they're pretty good. So it's semi-quantitative. So you might have plus or minus 20 to 30%, but does that matter when you're looking at 20 part per trillion plus or minus 30%? Not really a big deal. Sure. Sure. Yeah, you know, one of the problems was you want to do this when you're having complaints, right? Because you want to capture that odorous plume. If there aren't any odorous plumes, you don't have anything to capture. So what do you compare back to the facility? So it's really important to have the right meteorological conditions to capture representative data. And that was the problem with this study for the first week, that the meteorological conditions were not conducive to capturing plumes. There were no 1,100 odor complaints a year. The week we go, the first week, not a single odor complaint. We drove around looking for plumes for hours. Okay? Couldn't find any. The second week, the wind shifted, and sure enough, we were able to capture plumes. So. Actually, I don't like to say, but believe it or not, the wastewater treatment plant, where was nothing. You'll sit outside that fence line and you'll catch some odors. But like I said, sulfur doesn't get very far, especially oxidized sulfur. That's the primary means of removal is you add oxygen, it becomes polar. Oxygen is very electronegative. You create a dipole. Dipoles become miscible with water. They hit a water molecule, they go in, they drop out. That's how forest fires too. Most of those compounds are alkanes and aldehydes. They get converted to acetone and acetic acid. Those are the two main dropout components from forest fires. So you go downwind of that, and it's all converted to those, primarily those two compounds. And then rain takes it out. Yeah, it's Sartorius, Eumetrix. Yeah. Yeah, it is. They have good training modules in there, but they're also very good. They'll sit down with you and go over your data set and teach you how to use it and explain what's going on. Or you can hire them to do deep data analysis. That's what we did at first until we got familiar with it. Yeah, Sartorius, Sartorius. And you can talk to Bob Davis, is really good there. He's the salesman, but he gets you to the right people. There it is, Sartorius. It was formerly owned by MKS Instruments, that software, Eumetrix it was called, and Sartorius bought it from Eumetrix. Thanks. Okay. Well,